starting off with Chapter 2. Chapter 1 is something that you can review. We are going to go back to bits and pieces of it throughout the semester. It's sort of an introduction to power systems. It touches on a lot of the stuff from the PowerPoint. It also touches on a lot of stuff that I feel like might be better if we just discuss it later. So it's a good thing to read over, take a glance at it, but the real bulk of the material in terms of like the equations and the technical material starts at the beginning of Chapter 2. So, right, Chapter 2 is really just a review. I know we said the other one was a review as well, but this is a review of phasors and AC systems. So a lot of stuff that you probably should have seen in circuits and all that type of stuff, but we're going to be using it a lot here, so it's going to be important that we make sure everything is fresh. So I think Section 2.1, because I have my notes from last year here, and Section 2.1 I think was just some text, but Section 2.2 is phasor representation. So that's going to be a big part of this class, is using phasors. Does anybody know what a phasor is, or can tell me what a phasor is?
Value that has magnitude and angle.
Yeah, so it's a way of representing the steady state of an AC wave in a complex but more commonly a polar form, which assumes the frequency and therefore allows us to represent the AC wave simply as the magnitude and the angle, right? So in steady state AC problems, we will be able to assume a constant AC frequency. Now, depending on how far we get in this course, we may touch upon transients a little bit, especially when we're in synchronous machine modeling, but it's probably not going to be a huge part of what we do. So, like I said, phasors will be good enough, quote-unquote good enough for us 99% of the time. And so just a little bit of a review of, well, this is not a review, but an overview of the types of notation we're going to use in this course. So we're going to use actually two different types of notation. We're going to be using what's called single subscript as well as double subscript. You're probably more used to seeing the double subscript, and we'll introduce the single subscript later. But, right, a reminder of the passive sign convention, right, if we have a two-port network with voltages VA and VB, it has potentially, let's say, a resistance and an inductance along the line. So we have VA at one end, VB at the other end. Then what we can say is that the current flowing in this direction, that would be represented as IAB, right, because it's flowing from node A to node B. And the voltage across here would be VAB, right? That's nothing new there. It's just our convention for voltages and currents. Okay, so now, then talking about the phasors themselves. So how is a phasor defined from the time domain description of an AC wave. Okay, so we have, right, the time domain description would be VT, let's assume it's a voltage. We'll have an amplitude, which I'm going to write as square root of 2 times magnitude of V, where this is the RMS value here. Right? So we know that the RMS magnitude is equal to the amplitude divided by square root of 2, so I can kind of reverse that and define the amplitude in terms of the RMS value. Then we also have, right, cosine or sine of omega t plus whatever the V value is, where this, and I'll add a little V here, and this represents the phase. Okay, so now how do we turn that into a phasor? So we take that, and now what we have is that V, and I'll use that little arrow to represent the fact that it's a phasor or that it's a complex value. That's going to be equal to magnitude of V with an angle of theta V. So in most of the problems that we see in this course, you're not going to even start off with a time domain representation. It's going to just skip straight to phasor. And right, so the arrow, this means phasor or complex representation. So, now what is the advantage of using phasors? So, right, we can use phasors, spelled that wrong, but whatever, it's supposed to be an A. We can use phasors, or we do use phasors, because they make, well actually let me ask you, what's the advantage of using phasors? I'll go with some.
So it's basically so that we can swap in and out of like the Cartesian and polar formats. So that way when we're working in AC, we can just use the complex notation for, or imaginary notation for reactive elements. Yes.
I could parse that down a little bit and say it makes the calculations way easier, right? If we try to do all these calculations with AC power and power factor and all that type of stuff, doing that with, you know, this type V of t times I of t and having to deal with all the time and the omegas, it just makes the calculations way more unnecessarily complex. So when we represent it in a phasor form, like you said, it allows us to represent resistances, our impedances in a certain form, our voltages and our currents, but in the end it makes everything a lot easier. So if we take a look at, there's an equation from the book, it's equation 2.3, and so it essentially represents an RLC circuit in the time domain. So what does that look like, right? And let's just assume that they're all series elements, because I'm not going to draw the circuit. So we have R I of t, right? That's the voltage across the resistor, plus L di dt I of t, right? Plus 1 over C, the integral of I of t dt, equals, shifting down here, right, so that is a time domain representation of an RLC circuit. It's not going to be as easy to solve as if we put it into the polar form. So the polar form, it looks a lot nicer. That's going to be R times a phasor representation of I plus L j omega phasor representation of I plus 1 over C 1 over j omega phasor representation of I equals V. Okay, I never finished my sentence. Because they are easier to solve. Okay, this is a lot nicer. Okay. I'm going to start a new page because I actually want to type in the other direction.
Can we see the last one real quick?
Sure, yeah. From this point on, I'll keep a single document. It's just that I want to turn the iPad sideways. It's easier to write. Yeah.
And these will be uploaded to your website?
Yes. Yes, they will. I'm still figuring out what the best way to do it is. I'm probably just going to do a dump, meaning that everything will be dated, but I'm not going to split it up into separate pages and try to make some really nice document. It's as easy for you guys to see it like this as it is any other way. And it'll be in a PDF. I think when it transfers it over to a non-OneNote, whatever the name of this application is, it just displays as a PDF. And you can already see, if you go to my website, there's essentially a version of these notes from the board that's already available, and it looks forward if you want to see what we're going to be learning in a couple weeks or something like that, or the next class. Okay, so let me do this now. So give me more room to write. Okay, so now what's the relationship between polar and rectangular forms? Again, I know a lot of this stuff you've definitely seen before, but just want to make sure we're all on the same page. Essentially, right, the relationship between them boils down to trigonometry, right? You have, let's say we have an x-plane or a real plane and an imaginary plane. Okay, so this is real and this is imaginary. And then a phasor would be represented as some sort of a vector in this space. Okay, and so what we could do is we could represent this as, we could say this is the phasor I, and it has a magnitude, not a V, it would be I. It has a magnitude of I, and it has an angle of negative phi. All right, so now how do we define that in the polar form, right? What you would see is that the length of this vector, so from here to here, right, that length is going to be the magnitude of I. the angle here, that's going to be the angle phi. And then if we want to get the real and the imaginary portions of it, right, we need to see how is it projected onto the x plane. So the real component of I will be equal to, anybody know what that is off the top of their head?
Magnitude I times cosine theta.
Yeah, right. I mean, so magnitude of I times cosine of theta. You could also write negative theta, but again, for the cosine, right, it doesn't matter because the projection onto the x-axis would be the same. And then if we're worried about the the imaginary component, so the imaginary component of I will be equal to magnitude of I sine of theta. One last thing, right, is that you can calculate theta. Now this is not theta, this is phi. Sorry, I keep mixing up my Greek letter names. Right, this is equal to the inverse tangent of the imaginary portion over the real portion of the vector. And another note is, right, Pythagorean theorem applies, and so the magnitude of the vector is equal to, right, the square root of the real component squared plus the imaginary component squared. All right. And I made a mistake. Should be negative phi over here because the negative definitely matters for the imaginary component. Okay. So moving on to some more review, but stuff that is going to be really important for this class. Now this is a question that I always try to hammer home in electronics, and I still sometimes don't get 100% response. So what are the two components of impedance? This one's easier. Impedance is... Sorry, well, your answer is right. That's true. But what's the? Maybe I should clarify. What are the names of the real and imaginary components of impedance?
Resistance and reactance.
And then admittance is 1 over impedance, right? This is the one people have trouble with. What are the real and imaginary components of admittance?
Susceptance and
Conductance.
Yes. So please know those names. They're going to come up a lot in the text. They're going to come up a lot in this class, more so than other classes that you've taken. And you don't want to be like looking back and forth every time. But honestly, it's going to come up so much just by the nature of the class. You'll memorize it. Okay, so quickly, let me write it. So Z, right, is equal to R plus JX, which is equal to resistance plus J times reactance. You can represent impedances and admittances in a polar form. You may do that sometimes for calculations. There's no inherent names for, at least not that I know of, inherent names for those two components. Okay, then we have Y, which is our admittance. That's equal to G plus JB. And so that's going to be conductance plus J times susceptance. All right. Now, how do we define the components of Z? and then I'll put comma, from common passive elements. Or passive, well, elements is a fine word. Right, we all know for resistance, that's going to be represented by physically what component? Resistor, right? Reactance is going to be some combination of, and let's just assume basic components for right now, is going to be some combination of inductors, inductance, and capacitance, right? Now, you can have equivalent inductances and capacitances, you know, inside of different components like transformers and motors and all that type of stuff, and you might represent that as a reactance when there's not really a, you know, there's not some inductor that you can go touch inside the device. But just speaking strictly in like the most basic terms, right? So we know that for a resistor, the resistance directly transfers over, and that will be the resistive component of Z, which is R. Okay, you have your inductor. Okay, and so that has a value, we'll call it ZL, so that'll be the inductive component of the impedance, and so that's equal to J omega L. And then we have the capacitive element. And anybody remember what that's equal to?
1 over J omega C.
Yeah, 1 over J omega C, which is the same as negative J over omega C. If you want to calculate the impedance in a polar form, right, the basic, well, I don't think this equation is really worth writing. Essentially, you take, it's the same thing, Pythagorean theorem and inverse tangent. I have a version of the equation where it puts it in terms of R, L, and C, but really that's not a very useful formula because it would depend on what the circuit is. Okay, and what if we have impedances in parallel? This I'm not even going to write. If we have impedances in parallel, it follows the same rule as resistances in parallel, right? Z1 in parallel with Z2, Z1 times Z2 over Z1 plus Z2. Okay, so let's move straight into an example. So this is example 2.2. Okay, it asks us to calculate I1 of T in the circuit below. There is an example 2.1. It just asks you to calculate Z for a couple components. It's like inductor. It's essentially J omega L and 1 over J omega C. So that you can take a look at on your own if you have questions. This one is a little bit more in depth. Okay, so give me a second to draw the circuit here. So we have V1. Okay, resistance. We have an inductor. Then we have a shunt inductance. Okay, and then they, like most problems in this book, are going to go ahead and just skip to defining everything in terms of resistance and reactance. Even if it shows like the symbol for a capacitor or an inductor, 99% of the time it's just going to put it in terms of ohms. When we get further on into the textbook, we're actually going to move to another notation, which it's no longer going to be in terms of ohms, but it's going to be in terms of per unit. So there'll be a nominal impedance defined for the system, and then all the other impedances will be defined as 95% of the rated impedance or 25% of the rated impedance. Okay, so this is 7 ohms. This is J 0.2 ohms. This is J 15 ohms. This is J 0.5, and this is 0.3. So all the, as you would expect, all of the inductances have a J, right? And all of the resistances are real. So, I mean, just to practically make sense. So like I said, often they'll skip straight to defining things in terms of reactance. There's two currents that we are concerned with. There's I2 and there's I1. Okay, so how are we going to solve this? I'm not asking for numbers, but just the basic procedure. How would you tackle this? Yes.
Get the series resist equivalent for that combination of the parallel. That way we can one, get the voltage node at that point, so that makes it easier to find I2, and then we can just add them all up to get I1.
Yeah. So the good thing about these types of problems, when they're linear, and this is still a linear problem, is that we're just treating them the same way as we did problems from ENG212 from circuits. Okay? Everything is going to be in terms of phasors and in terms of impedances, but we're just going to, where in ENG212 we often had just real numbers, right, because we were dealing with DC 99% of the time. Now we're going to be using phasors. But all the other methods that you learn to solve are going to be exactly the same. So for these types of early problems, you can just imagine that it's a DC circuit, and how would you have treated it before? Right, like you said, combine the two branches, impedances together that are in parallel. Then you can combine it in series to get a single equivalent impedance for the entire network. And then you can go ahead and divide. I'm assuming they must give us V1, or else we can't really solve this. I think it's on the next slide. There's also one other. They call this IM. I don't know why they call it that. IM. Maybe middle. Okay, so let's parse through this. After this chapter, we're going to start diving into three-phase circuits, delta, Y configurations, power factor, the very beginning of power factor correction. So it's really quickly going to verge off into stuff that you haven't seen before. So just pay attention to this part. Make sure that you're up to date on everything. I know, again, a lot of the stuff you've seen before. But you really want to be solid on these basics before we start applying them, like over and over, pretty heavily. The circuits will blow up quickly in terms of size, and you'll be dealing with lots of phasors and everything all at once. Okay, so the first thing we're going to do is, we'll combine the series elements. So that'll be for this branch right here, the 0.2 and the 7. So that will give us this impedance, which we'll call ZA, and that'll be 7 plus J 0.2 ohms. Next thing we're going to do is combine the parallel branches. Okay. Later on, I'm not going to expect you to be doing all of these calculations by hand. I think your calculators can do these complex, like they can multiply and divide by complex numbers, right?
Yeah.
They should be. Okay. So later on, you'll just do it that way. In the very beginning, I do want us to do a couple of these by hand. And you know, like I said in the beginning of class, we are going to be having quizzes pretty often. So our first quiz will be scheduled for a week from today. It'll be this upcoming Thursday. And on Monday, I'll talk about exactly where the stopping point in the material is with regard to, like, you have to study up until here in order to, you know, to have your stuff together for the quiz. But the first quiz, right, that's going to be the one that could ask you more of this, like, problem like this, doing stuff by hand. After that first quiz, we'll probably be past that point and you won't see too much of that anymore, and it'll all be more complex problems, but you'll be using your calculator. Okay, so we need to combine a J15 ohm reactive element with the ZA, which we just calculated. So that is essentially addressing this whole chunk right there. Okay, so what is that going to look like? That's going to be J15 times 7 plus J0.2 over J15 plus 7 plus J0.2, right? Z1, Z2, Z1 times Z2 over Z1 plus Z2. All right, so for the numerator, we're going to have to perform multiplication. For complex numbers, normally, how do we do multiplication? In what form?
Polar.
Polar, right? In polar, it's easy because, right, if I write it real quickly over here, right, Z1 times Z2 equals the magnitudes combined, and then the angles summed, right? And addition and subtraction we normally do in a rectangular form because you can just parse out the real and imaginary components and you can subtract or add them. So that's what we're going to do here. Actually, there's an exception that for the numerator we don't have to do this in a polar form. We can keep it in the rectangular form. Does anybody know why that is?
Because there's only, each one only has a imaginary part.
Yeah, well, so, yeah, exactly. Because the second element doesn't have real and imaginary components, multiplying out the j will only take 2 seconds. Whereas, right, if you had two components, you would have to, multiply it out and then combine the real and the react, and that becomes a whole pain. But we can just multiply the j out, so it'll end up being j15 times 7 minus 2, because j times j is equal to a -1, and that'll be then minus 15 times 0.2. So for this case, it'll probably make more sense not to do that. So what we'll end up with is, right, J15 times 7 minus 0.2 times 15. And then on the numerator, or on the denominator, we will just add. And that's easy. So we'll end up with 7 plus J15.2. So what I have in my notes, because I did these, I think 15.7, 15 times 7 is 105. If someone wants to check that with a calculator real quick, I appreciate it. And 20% of 15 is 3.
105.
That's right?
Correct.
Perfect. Okay. So what we end up with is -3 plus J105 over 7 plus J15.2. Okay. Now, from here, so for the division, we will need to go to the polar form. All right, so let's do that. All right, and I'm going to write it out in its length. Okay, so first thing we want to do is get the magnitude of the numerator, right? So what's the magnitude of the numerator going to be? It's going to be the real squared, or so the square root of the real squared plus the imaginary squared. The real component of the numerator is -3, so that's -3 squared, plus 105 squared. Okay, so that's going to be the magnitude of the numerator. The magnitude of the denominator, right, give myself some room, will be 7 squared plus 15.2 squared. Okay, then to find the angles, what function are we going to use to find the angles?
Inverse tangent.
Inverse tangent. So the inverse tangent of our real over imaginary, 105 divided by -3. And then our inverse tangent,
Should it be reversed?
uh,
Yeah. The real's 3, -3.
yeah, imaginary over real.
Oh.
So 15.2 over 7. Okay, now one thing that I always recommend for when you're doing these the inverse tangents, is you have to keep track of where you think the phasor is supposed to be, okay, where the angle is supposed to be. Because the inverse tangent of -105 over 3 is the same as the inverse tangent of 105 over -3, right? The negative, it doesn't know. So the way I like to do it is, right, I know that this has a negative real portion and a positive imaginary portion. So that means that I should be here, right, somewhere in that quadrant of the and then when both are positive, I know that I should be here. So if my angle that I come up with doesn't end up in the quadrant that I expect it to be in, then I know I have to add the 180 degrees in order to account for it. For the second one, I'm not too worried, because when they're both positive, when you don't have any negative numbers, you're going to end up in the right quadrant regardless. Okay, so what are the values that we end up with? And again, please feel free to check via calculator. So I think 105.05 for that, which makes sense because we're taking the magnitude of a really, really long y component and a really, really short x component, which, right, it's going to be essentially the same. And then divided by, I have 16.73, which again sounds right. Okay, the angles. So can someone tell me, when they type it into their calculator, they do inverse tangent of 105 over -3, what does it spit out?
-88.36.
Okay, -88.36. So that puts us right down here, right? So that's not, right, -88.36 degrees would be down in the fourth quadrant. So this is a case where that's not, right, what we want. We need to add the 180 degrees in order to, yeah?
Yeah, inverse tangent is limited to the first and fourth quadrants, so like if you
Yeah.
have anything outside of that, just have
Essentially, if you have the
Yeah.
denominator being, yeah, okay. So, so we flip it, and I have 92 degrees. And then we don't have an issue for the denominator, 65.3 degrees. And when we lump that all together,
You just subtract those, right?
yeah, sorry, I should have stated that. Yeah, for these two, this is going to be 92 minus 65.3 degrees. And then for these two, it's going to be 105 over 16. That's how you deal with the division. And so this value, we're going to go ahead and call ZB. And so ZB is the equivalent of all of this right here. All right, next. Combine the last series elements. Okay, so the Z total, or the Z equivalent, will be, what's the top? It's 0.3 plus J 0.5. Plus 6.27 cosine of 26.3 degrees plus J 6.27 sine of, I ran out of room, so I'll just put that same angle.
Professor?
Yep.
26.7 degrees?
I have a value I calculated last time. It could be off. Was there a mistake? Is it 26.7? Can someone run the numbers again?
Yeah,
Yeah, it's 26.
because like 0 minus 3.
Yeah, you're right. Yeah, 0 minus 3 should be 7. Okay, that's fine. I'm mostly relying on the numbers from last time, so yeah, please back me up with the calculator. And last time I ran it, it was the students that were doing the calculations. So you can blame them, not me. They were the ones that got it wrong.
I blame you for blindly following silly students.
This is the hierarchy. This is the way it works. All right? Okay, so step 4 is going to be to calculate the I. And it does give us V1, even though I didn't write. Well, I can go back up and write it. V1 is 120 with an angle of 0. That's what it is. Okay, so I1.
Sorry, what's the fee there on the end?
It's the same angle. I just ran out of space, so I just put phi, and then that's what the blue arrow is. Okay, so we end up with, oh, I never added all these together, sorry. After we add all those together, we end up with 5.92 plus, oh, actually, we might have to recalculate the imaginary part because I have it calculated was 26.3 degrees. So could someone tell me what J 0.5 plus this component is?
I got it as 2.79 J.
Okay.
Oh, the total?
Yeah, the total.
Oh,
So then add 0.5 to that.
yeah. So that would be 3.29.
Okay, and then if we convert that to a polar form, which we're not gonna, we did that a lot, so we don't have to do that again. Again, checking, well, you might have to rerun it because my number was slightly off. I have 6.77 with an angle of 29. It's gonna be really close to that. Is this thing running? So yeah, I'm going to try to post the lectures online. It's actually not so much for this semester. I just want to have a record actually for future semesters in case a class gets missed or something like that. I can kind of keep moving and post it. Say like, look at this.
6.78 with a degree of 29.
6.78 with a degree of 29. Yeah, it was 0.01 off from what I got the last time. Okay, and then last now, we'll calculate the I. So we'll use Ohm's law. It actually should be a little bit hot, a little bit lower than 17.712 because I used 6.78 instead of 6.77.
It's
Basically the same. Okay, I'm just gonna leave it there. All right, so 17.712 amps. So that's the first type of problem that you could potentially see on a quiz or an exam. Yeah.
How important is it that we use the vector symbols for this stuff?
Oh, I mean, I'm not going to be real picky about that type of stuff. I'm not looking for stuff like that. I mean, that's like a style notation type thing, but if you give me the answer, I1 equals 17.712 with an angle of negative 29 degrees, and you forget the arrow, I just won't pay attention. So, and it's actually more important for me giving the notes because it's important for you to understand. Okay, this is a vector, this is a magnitude. So I try really careful to keep it straight on my end. Yep.
Just making sure, like, we should round to like the hundredths for like the magnitude and like the tenths for the degree, or hundredths for the degree as well? Or?
So I am not applying significant digits properly. That is not one of the objectives of this course, so I'm going to give a blanket statement that you should do better with significant digits than I am doing in this example. Yeah, technically, you should not include the third decimal place for the magnitude answer. But no, there's no requirement like hundredths or, you know how it is. In most engineering classes, whatever the calculator gives you, that's what we put up there. So another thing that I'm not going to be very, very picky about. I mean, if the answer is like 0.00342, don't give me like 0. Don't round it too much. But whatever you do in the rest of your classes when it comes to these types of numbers, do the same thing. I'm sure it'll be fine. Significant digits, we'll save that for the end of the class. All right. So next, section 2.3. which is power, reactive power, and power factor. Let's see if I can draw some sort of a separator here between the sections. Because I'm sure when you're cycling through all these notes, it'll start to blend together. Okay, so in this section, we're going to do a couple things. We'll calculate instantaneous power. We're going to look at the effect of phase difference between these waveforms on PT. Okay, the waveform specifically. Because what we'll see is that the shape of the waveforms for the instantaneous power will be affected drastically by whether these VT and IT waveforms are in phase with one another, completely out of phase with one another, or there's some shade of gray in between. We're also going to calculate the average power. And move on to what's the word I want? Not notation. The terms. So we'll introduce some new terms. Okay, so we're going to start off with the table below, which is sort of going to compare what PT looks like, instantaneous power, and average power for the cases where VT and IT are in phase and out of phase. So what is that going to look like? So we have, and this is going to take me a second to draw, so we have PT, instantaneous, or sorry, the frequency of PT. Okay, we have the instantaneous power, which is just the PT waveform. Try to give myself enough room here. And then average power.
Professor?
Mm-hmm.
By average power, do you mean RMS power or like true average power? Or is that
True average power.
Alright.
We're gonna dive into all that in a second too. So right now, when we're saying average, we're saying the actual. You take the integral, yeah, and divide by t over the period of the waveform. I need to take a 2-second break. My hands are getting tired. That's the one bad thing. Like writing on the board is tiring, but like hunching over and writing with this thing, 'cause it's not a real pen, so it like kind of is okay, but then it.
I find it nice to zoom in a lot.
Yeah, that's true. But then you guys won't be able to see anything. Yeah. It needs a little bit of resistance. Like if it didn't slide so easy, I feel like that would make it feel more like a pen. Okay, so we have the one case where it's in phase. All right, so the voltage and current waveforms are in phase, and then the other case is going to be not in phase.
Professor, can you explain what you mean by the first two rows on the first column? What is?
So essentially, right, scroll over here for a second. We take our VT and our IT waveforms, right? In order to calculate the instantaneous power, we're going to multiply the two of them together. And that's going to give us a waveform that looks like this, right? So the first row is what is the frequency of this. The second row is what's the waveform shape look like for a P of t instantaneous. And then the third is what is the average value over a single period, or well, it's steady state, so all the periods will be the same.
Okay, thank you.
Okay, so instantaneous power is going to oscillate at a frequency of 2 omega 0, regardless of whether the V and I waveforms are in phase or not in phase. So omega 0 or omega naught, that is the frequency of the voltage, as well as the current, right? For phasors, well, first off, for the problems that we're going to be looking at, right, by default, the voltages and the currents will have the same frequency. And then also, since we're going to be doing this in a phasor notation, they have to have the same frequency. So V naught, if we're talking about electricity from the wall, it oscillates at 60 hertz, and so therefore our instantaneous power is going to be oscillating at 120 hertz. Okay. Instantaneous power is going to be greater than 0 for all t. So if I were to imagine what this looked like, it will look like this. Greater than 0. Okay? If they're out of phase, this is not true. And so what you could end up, well not could, you will end up with is some portion of the waveform dipping below the y-axis. Sorry, the x-axis. Now, the average power is going to be, for the in phase case, will be a straight line at the maximum. And that's not really, that phrase might be a little bit misleading. So, the average power will be a straight line and represents the maximum value possible. What that means is that when the V and I waveforms move out of phase, you'll see the average power drop. So the average power is maximum when the two are in phase. Okay.
Still a straight line, right?
Yeah, well, I mean, I should, you really don't even have to say that. I mean, if it's average, it's going to be a straight line because that's the, right, you're getting a single value, you're integrating and taking the dividing by period. So, I'm copying from the notes I had last time, and some of the stuff, I guess, was part of the discussion. Yeah?
And would it be like 0 in the case that it's purely reactive, like average power? If your load is purely reactive, so that way you would have like a phase of 90 between your power.
Yeah. Yeah. Then all the power will be reactive. Well, we'll get to that in a second. Yeah. I mean, because if you talk about, right, it being at maximum positive, and then you can go all the way down to maximum negative, there is the case where they're completely out of phase, and you end up with the 0. Okay. So I have a note here about including a picture from the book. Does anybody have the book in front of them? No. All right, I'll try to find that picture and include it in the notes. I guess, I didn't bring my book with me either. Actually, I have it in my office. Next time I'll remember to bring it. Okay, so now let's go and actually do some of the math. So this is sort of just an introduction to how the cases of phase versus out of phase are going to affect power, and now we're going to go do some of the math. The main takeaway from this table here is that, right, average power is power that we can use to do work, okay? So you see that when our V and I waveforms move out of phase, we're actually losing the amount of power that we can get to do work, but we're not reducing the amount of energy that's necessarily being generated, right? So this first or second column here, the one that's in phase, is going to be preferable. And this leads us to the topic of power factor correction, which is things that we can do to try to bring the voltage and the current waveforms into phase with one another. All right. So now let's go ahead and define P of t mathematically. Okay, so first case, the two waveforms are in phase with one another. And so what that leads us to is we'll have a value of PT, which will be equal to V average times I average plus V average times I average cosine of 2 omega t. sorry, I gotta rewrite that. I mixed up two values. And I want to get the subscripts right. So V, what should I say? V RMS, I RMS, plus V RMS, I RMS, cosine 2 omega t. Okay. So obviously, right, these are the magnitudes, RMS magnitudes of the waveforms. And so what are these individual, how can we split this up? So this is going to be our average component. Right? And why is that the case? Because if we take the average of the entire P of T waveform, if we take the average of the second component, right, what's the average of a cosine? Average of a cosine is 0, so that's obviously going to fade away. So we'll just be left with the non-time varying component. So we have the average component, and then we have the time varying component with an average of 0.
So the first term's going to be the average power.
Yes. Okay, now the second case. So here, we'll see one difference. We'll have VRMS, IRMS, cosine of phi, we'll talk about what that is in a second, plus VRMS, IRMS, cosine 2 omega t minus phi. Okay, so first thing I'm going to do is define again the average component, right? So we have the average component and we have the time varying component. Okay, so now what is phi? Phi is the phase angle or phase difference between the voltage and the current waveform. So what we end up is this is equal to the angle of V minus the angle of I. And this, the second equation, will solve down to the first equation if we substitute in a value of phi that equals 0, right? The cosine of, yes?
The average of the time varying component of the out of phase case is 0 as well?
No, it's not. The average, both have an average component. This is the average component for the in phase, this is the average component for the out of phase. There's no omega t in here, so this doesn't.
I'm sorry, the time varying component.
Yes, again, right, anytime you have this cosine, it doesn't matter if there's a phase shift applied to it or not, you're going to have it.
The average will not be 0, correct?
No, the average will be 0. The average for this component and this component will be 0. Anytime we're taking cosine of something omega t.
Okay.
Right? Because the cosine doesn't have a DC shift. The average will be 0.
Okay, thank you.
Okay? And so when we plug in a value of phi equals 0, the cosine of 0 will give us a 1, so it'll collapse down to what's up there, and then same thing. The phi will equal 0, and so we'll end up with the same answer. Okay, so in previous classes I've gone through and done the VT times IT and calculated the whole thing out. It's a long process. It's rather tedious. I think they go through and do that in the book, so if you're interested, you can see how it actually separates into these two components. But I'm not gonna spend the time to do it here. It takes a lot of time. All right. So the one thing that we want to note so we observe that the average component of PT is dependent on the phase difference. And is maximum when phi equals 0. So similar to what we showed in the table, right? Average power maximum when the two are in phase. Okay, so now, next thing that we're going to do is discuss how average power relates to complex power. Or what we, probably a better term, is complex or apparent. Okay, so apparent power. And so let's go ahead and parse out those definitions first. So apparent power, is it two P's? Yeah, it is. Apparent power. Apparent, or also we'll use the term complex power, is equal to, so we'll represent it by the letter S, and it's equal to voltage times current conjugate. So we're taking the conjugate of the, well, actually it's the same thing as taking the conjugate of the whole thing. But and does anybody remember what taking the conjugate, what that does?
Flips the imaginary form.
Yeah, that's all you gotta do. If it's in rectangular form, flip the positive to a negative. If it's in polar form, you flip the sign of the angle. Sorry, one second. Okay. And for this definition right here, we're going to be using these. This is how we're going to define I and V. I just want to get those defined. So I will be equal to what we, so similar to before, angle, so magnitude of I and angle phi sub I. V will be equal to, right, this. So the sub scripts will tell us whether it's associated with the voltage or the current, and if I go ahead and break that out, right, it'll be equal to magnitude of V times magnitude of I times the angle V minus the angle I. Right, so that's the definition of complex, or also known as apparent power. All right, so now let's take a look at,
Sorry, the angles get added, is that?
well, they get added because they're multiplied, but then they get subtracted because you're taking the conjugate, right? So if the conjugate weren't there, it would be phi v plus phi I, and then the conjugate flips it.
Why isn't the PV negative as well?
So
Oh, okay.
Yeah.
Oh, it's I conjugate?
it's I conjugate, yeah. All right, so I don't think there's, I have a phasor diagram that I drew last semester, but I don't think there's any need. You guys know what that looks like, so. Okay, so complex power. How is it broken down? And when I say broken down, I mean how do we split it into its components? And so, right, S is equal to P plus JQ, which is then equal to real, try to write that more clearly, real power plus J times reactive power. Okay, we can also write it in a polar form. Well, before I do that, let's talk about what reactive and real power represent. So real power, let me leave some space to discuss reactive power. I'll do that second. Okay. Real power is the average of the instantaneous power over T. And it represents power that is usable and may be applied to work. Okay, so when you run your vacuum cleaner, it's the amount of real power that you're drawing from the wall that's going to determine how much torque and rotates that piece there. Okay, same thing with lights or whatever. Reactive power, does anybody know, besides this mathematical definition that we gave, what reactive power represents? No. The name actually gives you a clue. So what do we call inductive and capacitive components? We call them reactive components, right? So, sorry? Okay, so when you first, in ENG 214, when we talk about reactive components, we talk about the startup and the shutdown transients, right? So what ends up happening is, in the very beginning, before you reach the steady state, power goes into those reactive components. Then when they reach the steady state, that's when the inductors start acting like short circuits and the capacitors start opening like open circuits, right? Before that, during the transient period, the inductors don't act like a short circuit. They store energy, right? They have to get charged up. So reactive power is the energy that's being stored within the reactive component. It's constantly being charged, just because we're talking about AC, right? It's constantly being charged, discharged, charged, discharged. It's the energy that creates a magnetic field, gets released from the magnetic field. Creates the electric field, discharges that electric field. So it's not lost power, because you actually will get that small piece back if you ever eventually shut down the network, right? The shutdown transient would release that energy back to you. But in the steady state, it's not usable. Yes?
What do you mean goes back? Where does it go back? To the generator?
It would run. It would run as a current along the lines. So let's say
to the load.
To
the load.
Yes. Yes. If you have a generator running to an AC network, running to a load, you shut off the generator, okay? In a purely resistive network, right, there would be no shutdown transient. Everything would be immediately off. In a network with reactive elements, right, there'll be a transient, a shutdown transient, which will be when the energy is released from all the reactive components, and that energy would flow through to the load.
So that's why my speakers bump when I turn off the amp.
Yes. Yes. I mean, I can't say that's the only reason. I don't know if there also might be a time lag in some of the components. I'm not an expert. But yeah, definitely the shutdown transient will be part of it. Okay. So this is stored within the reactive elements. Okay. So now how do we define the real and reactive power? As you would expect, right, we know S is equal to V angle theta V times I angle negative theta I, right, because that's the conjugate. And so if we were to break that down into the real and imaginary components, we would end up with that times that. The real component would be the cosine of theta V minus theta I. Okay? Plus, dot, 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 I'll put it below it, dot, 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 plus J, again V, I sine of theta, I keep calling it theta, sorry, phi V minus phi I. So this is Q, the same Q we have here, and this is P. And this little piece here is the magnitude of S. Yeah.
And as before, magnitude V, magnitude I are the RMS values of the. Alright.
Magnitudes RMS. We're not going to say it every time. It's across the board going to be the RMS value. Okay. Now, one last value is going to be the power factor angle. And so the power factor angle we're going to represent simply as phi, and that's going to be that phase difference that we've been referring to so many times. So power factor angle equals 0 means that the voltage and the current waveforms are in phase with one another. What are the units? No, for that one. I was talking about the real and reactive power. So for P, you guys all know that one, right? That's going to be watts. For Q, anybody know what that one's in? VAR. Which stands for volt. Spelled that wrong. Volt, amps, reactive. And then S, you can simply refer to in terms of volt amps, which is kind of a cheap unit because it's just stealing two other names and combining them together. All right, so now we talked about power factor angle. We talked about power factor angle, sorry. We're going to talk about another very important value, which is simply the power factor. Okay, so the power factor is the ratio between usable or real power and apparent power. So power factor. Equals P over magnitude of S. It's going to be equal to the cosine of the power factor angle. And if you go back to some of the equations above, you'll see why that's the case, right? Because, and I'll write it again here. If you think about it, right, P, right, is equal to the magnitude of S times cosine of the power factor angle, and so then we just move that to the other side, and you end up with that power factor. So power factor has a maximum of 1, right? Power factor can't exceed 1 because that would mean that there's more average or real power than there is complex or apparent power, which that can't happen. And a power factor of 1 means that the voltage and current waveforms are in phase with one another. Power factor correction, which we'll get to in a second, is any sort of method that we use to try to bring power factor up to 1. Yeah?
We have a symbol for power factor.
Yeah, it's just V.
I'm sorry?
Oh, no, there's no symbol for it. Not that I'm commonly using. I would just say PF. A lot of times they'll just write, like they'll say maximize cosine phi or something like that. It doesn't have its own symbol. You can make one up and become famous. All right, so next question. And let me throw that question out before I get into it. So why is maximum power factor, high power factor desirable? You guys answer a lot. Let me throw out somebody else. Anybody know? If not, then I'll come back to you. Yes?
I mean, obviously you would want more usable power than reactive power, like that's being essentially not used in the system.
That's one good reason, yeah.
Wouldn't you minimize the loss in the transmission line?
That's the key, right there. So the more the current that you have to transmit along the lines is proportional to the apparent power being transmitted, not proportional to the real power being transmitted. So that means that the loss is also, right, again, P loss equals I squared R, right? The loss is going to be proportional to the complex power being transmitted and not the real power. So, reactive power, you're paying a price for, okay, there's a penalty associated with it, but there's no benefit associated with it because, again, you're not using it to do any work. So,
Like batteries.
huh?
Unless you like batteries.
Yeah. So, all right. So that's the main core reason. Let's go through and write out some of the math. Right? We know. So first thing we know is that transmission line loss is going to be equal to magnitude squared R, okay, of I. And the reason why it ends up being magnitude and not the value is because of the conjugate value. We can go through and show that, but
It's simply a silly question, but is the loss is the loss maximized when both the power or the voltage and the current lines, are they out of phase? Is it when they're more out
Yeah.
of phase that it'll be you're gonna lose more power?
no, actually, the loss is proportional to the amount of complex power that you're transmitting. So that will stay the same. If it's all reactive power or it's all real power, if the S value, magnitude of S stays the same, the loss will stay the same. The difference is how much benefit are you getting from that loss? Okay, it's like I'm going to pay $5 for this whatever. Am I going to get 5 apples that I can use and I can eat? Or am I going to get 1 apple, or am I going to get no apple? So that's the difference when you talk about the phase versus in phase. When you're completely in phase, you're getting 5 apples back that you can eat. When you're completely out of phase, you're getting no apples, right? You're transmitting this power, it's all reactive, none of it's usable. And so you have the loss, you're losing power and not using any of it. So yeah, so the magnitude of the loss, we'll see in a second, is dependent on the magnitude of S, not the magnitude of P.
Wouldn't, going back to when we were talking about the conflict with AC and DC, wouldn't using DC, eliminate this complex situation?
Most definitely. That, if you remember back to the lecture that we gave, the PowerPoint, right, we talked very briefly about something called high voltage DC transmission. Okay, we didn't dive into it, but that is one of the advantages. If you can bump the voltage up very high, okay, using power electronic devices, you can't use a transformer, obviously, and you run at DC, right, then you get a very, very low loss along the line. So that's the reason why HVDC is normally going to be used for transmission over long distances. Let's say you have some nuclear power plant in a remote area. It generates tons of energy, but there's nothing to use it, right? In North Oklahoma or something like that, right? You can run HVDC transmission line to Dallas or to Chicago, but right, the disadvantages are it's going to be difficult to pull power off that line. You'll have to invert it and all that type of stuff. So it's normally going to be like an express train going from point A to point B.
But that's done.
It's done. More so in Europe than in the United States. I'll be honest, I haven't kept up on that too much. I'm sure that they built some more in the United States. It's expensive, and it's difficult to make money from it just because of the way the deregulated market is. There's not so much benefit, especially in the United States, from upgrading transmission resources. There's a lot of money from upgrading generation resources. It is used. It does exist in practice in industry. There are most definitely HVDC lines in use. Not so much in the US.
Yeah, I've seen video of a few plants like that in Canada, and it's basically like the equipment needed. It's takes the whole room.
And it's also you know, the more, there's not moving parts, but the more electronics you have, the more prone it is to failure and all that type of stuff. And also you have to have the need. I mean, there's not as much, like the Limerick nuclear station here in you know, near Philadelphia, there's plenty of load around here, so there's absolutely no need to do that. You really, there's a cost benefit there of, you know, are you transmitting it far enough to make it worth it? And then the other side of it is if you do a really good job with power factor correction, then you're negating the DC part of it, right? So if you can be very efficient with your power factor correction, then just do high voltage AC. But that sometimes is easier said than done. Okay, so the last thing we'll talk about here is why is high power factor desirable. So we know transmission line loss is equal to I squared R, magnitude of I squared R. And then we also know that I is going to be equal to the, so S divided by V conjugate, okay, which is going to be equal to P minus JQ over V conjugate. And then if we split that up into the magnitude and to the phase, we end up with the magnitude of I, right, being equal to the square root of P squared plus Q squared divided by the magnitude of V, right? Because you take the square and then the square root of the same thing, you end up, well, we already have the magnitude actually, you don't have to take any, we already have that value. And so, right, what we see, and we don't really have to, the phase isn't coming into play here, so we don't have to worry about that. So the main point, the main takeaway from this that loss and I squared, right, both will drop if Q is equal to 0. So that's the whole objective behind power factor correction. Now there are other advantages as well. It's not strictly a transmission issue. When it comes to certain types of equipment, there can be advantages to running at what we call unity power factor. That's the term for power factor equals 1. But the main one, and the main one we'll be focusing on, is its effect on losses. So now power factor, there's 2 different types, because power factor doesn't tell us whether the angle is positive or negative, right? So to give a full description, you need to refer to it as power factor lagging, meaning that the power factor angle is positive, or power factor leading, which means that the power factor angle is negative. And the way that you treat it, the way that you perform power factor correction, is going to depend on whether it's leading or lagging. And we'll get to that next.